My dear friends, welcome to Rajshekhar classes on applied data science with Python. This is lecture number 636. In this lecture, I will continue my discussion on recurrent neural networks. Before understanding this lecture, I request you to go through my previous lecture, that is lecture number 635. All these concepts I discussed in my previous lecture, that is lecture number 635. Just try to recall. This is time series prediction. This time series prediction is also actually a sequence prediction problem because the information is sequential, because one comes after the other. We have partially used the sequence information by windowing the data. Just try to recall all these things I discussed in my previous lecture, that is lecture number 635. Now let me continue my discussion on recurrent neural networks. The third thing is just what it says. Third thing that you often see is machine translation problem. It become very popular application. I can say it's a very popular application of deep learning in the recent past. Suppose if you give a sequence in let me say, suppose if you give a sentence in English, let me say I have sentence in English. Imagine I'm traveling to Spain. I want to give an English sentence. I want machine learning model to convert into Spanish. I have sentence in English. I need machine learning model which convert into Spanish. So what you have here is a sequence input. This is important. Your input is sequence input. Sentences that you are giving in English is in sequence, and the output that you have is also a sequence of words, isn't it? The output is in which language? Output is in Spanish language. Output is also is the sequence of words in Spanish. Your input is also, sequence is important here. Your input is also sequence of words in English. So machine translation is very nice example. I can say this machine translation is a very nice example where you have sequence of input and a sequence of output. Means in the context of input and output sequence is very important. These models are called, how can I call them, sequence to sequence models, which are basically I can say these are small variations of recurrent neural networks. So for lots of very important applications like determining a sentence, determining a sentiment of review. Just try to recall, we discussed the sentiment of a review in Amazon Fine Food reviews, isn't it? Whatever the review is, whether the review is positive or negative, it's great if you can use sequence of information. Of course, we are gotten around without using it. In the case of Amazon Fine Food review case study, we have not taken care of sequence of information. If you use the models, if you use the sequence information, if you use the sequence information, that models will improve dramatically, isn't it? But of course, in the context of Amazon Fine Food review case study, which we discussed long back, there we were not taken care of sequence information. If you take care of sequence information, their model performance will improve dramatically, isn't it? The stock market predictions, stock market movements, any sort of time series like we see just if you recall New York City tax, there is one case study which we will discuss in future. There is something like New York City tax cabs related case study, there also sequence of information is very important. That we will discuss. The data set what we see here is how many, actually in the New York City tax case study, which we will discuss in future classes, there also how many cabs would you expect at given location in future, given all the past information, which is very standard time series problem. I will discuss the standard time series problem in my future lectures. Machine translation happens a lot. The fourth application, which is very common again, is speech recognition. In speech recognition, input is a sequence in audio. We can find speech recognition, you can find speech recognition in Siri, Alexa, Google Now. Of course, my favorite is Google Now till now. I give a sequence of audio. It is basically audio sequence, isn't it? What it outputs me is a sentence in English. This is what all about speech recognition, isn't it? Yes, this is about all about speech recognition, all about, because audio is also a signal. Audio is also signal, which is a sequence signal. That signal, I can say it's a sequence signal, and you get an English sentence. This is very popular application. The fifth application, I can say, the fifth type of application is called, you input an image, and what it does is it captions the image and tries to give a sentence on what is there in the image. That's important. This problem is called image caption. So what it does is, you give input image, the output is basically, you give input image, the output is basically, I can say, output is basically an English sentence explaining you what is there in the image. So it provides you captioning to the image. So your input is just one image, but your output is an English sentence, which is a sequence. So there are all many popular applications of recurrent neural networks. Actually, in all these cases today, RNNs are this. Just see, if your input image caption means what, you give an input image, the output is basically an English sentence explaining you what is there in the image. That's important. Just if you observe you can see these are the very popular applications. You can see the applications of recurrent neural networks in NLP, time series, machine translation, speech recognition, and image caption. These are, I can say, these are very popular applications. You might wonder, why is image captioning is useful? Imagine Google providing you image search. Look Google image search. Image search can be just image search can be improved a lot. If you have an English representation of what is there inside the image. Once you have the contents of the image, because once you have this English sentence, it is almost it almost becomes like Google text search, isn't it? Image search can be improved a lot if you have English representation of what is there inside the image. I can say, if it is the case, once you have this English sentence, it almost becomes like Google text search, isn't it? Just like Google search. So Google image search can be improved dramatically, like captioning each of the images like English sentences, then using the Google standard text-based search on top of it. Now, because you know what is there inside the image, so you might wonder all this is great, but what is so important about it? Why it is so important? The core idea here is if your output depends on the sequence of inputs, not just the set of inputs, but the sequence of inputs, then we need to build a new type of neural network which gives important to the sequence of information. it somehow retains the information, retains and leverages the sequence information. That's important. It somehow retains and leverages the sequence information to perform better than non-sequence based applications. The next thing that you immediately get is, let's take this example to make it concrete. Let's say Amazon Fine Food Review. This case study we discussed long back, Amazon Fine Food Reviews, where you have literally sentences or sequence of sentences. Just try to recall, and you have to predict. This is your xi is a sentence. Let me say xi is a sentence. What xi is a sentence. Your yi is basically a two-class classifier, whether it is positive review or negative review, 0 or 1. Let's take one sequence. Let's take one sentence. Let me take xi is a sentence. Let's assume this sentence contains multiple words: xi1, xi2, xi3, xi4, xi5. Let me say xi1 is the first word, xi2 is the second word, xi3 is third word, so on and so forth. Since each of these is a word, let's assume this is my sentence. The phone is very fast. Then you might say, why can't you just use a multi-layer perceptron for this? Let's try to build a multi-layer perceptron, a simple multi-layer perceptron to solve this problem instead of RNNs. Now, what is your xi1? Your xi1 is a word. Now, I can represent this word by one hot encoding. Let's assume in my vocabulary, I have, let me assume in my vocabulary, I have 10,000 words. In my total vocabulary, I have 10,000 words. Xi can be represented as a vector, one hot encoding vector. How can I represent my xi? It is a one hot encoding vector. So xi1 is a vector. Similarly, xi2 can also represented as one hot encoding vector. I can say in general your xij, I can say your xij belongs to what is that r power 10k, isn't it? Yes. Why? Because we are assuming there are 10,000. Initially, what we were assuming, I have 10,000 words. That was our assumption, isn't it? It's a binary vector. I can say it's a binary vector. Remember, xi1 is not scalar. That is important. It is a vector because each of these, xi1 is a vector, xi2 is a vector, so on, xik is a vector. All xi1 is a word, xi2 is a word, xik is a word. Each word is represented as a vector of dimension 10,000. Now, you may say, why can't? Now, you may say, why can't you simply train multi-layer perceptron on top of it? Let's see. If we train a multi-layer perceptron, let's assume I have one layer. I have what is my sentence here? xi1, xi2, xi3, xi4, xi5. I have 5 vectors, isn't it? Yes, I have 5 vectors. Each vector size is 10k. So let's say this is my layer 1, this is my layer 2. I have softmax layer or logistic regression layer, and I get my yi, isn't it? I have two class classification. I have logistic regression. Softmax is generalization of multi-classes. So what I can do with my input is, here I have vector for xi1, here I have my vector for xi2, vector for xi3, xi4, xi5. This whole input now is, what is the size of each vector? xi1 vector size 10k, xi2 vector 10k, so on, xi5 vector is 10k, isn't it? This whole input, that's the whole input, is 50k dimensions. This is my whole input layer. I can say this 50,000k is the input layer. This whole thing is my 50k is of input layer, isn't it? In input layer, I have xi1, xi2, so on, xi5. You have bunch of activations. Let me say in layer 1 I have activation units. In layer 2 also I have activation units. Of course, the number of neurons in each layers, you can decide. Look, the structure here, 50,000k inputs here, because your xi consists of five your xi consists of 5 words. That's why you have 50,000 input. I can build a multi-layer perceptron like this, and I am still preserving sequence information, because the first word, the first 10k vector, second word is, the first word is first 10k vector, the second word is second 10k vector, my third word is my third 10k vector, fourth word is my fourth 10k vector, my fifth word is my fifth 10k vector. I am still preserving the sequence by putting the first word on top of the second word, on top of the third word, fourth word, and fifth word. But which is a nice argument. There is one problem, there is one key problem of this approach that I will discuss in my next lecture, that is in lecture number 637. Thank you very much.